The broadcast is now starting. All attendees are in listen-only mode.
All right. A little bit of feedback there. Let's take that from the beginning. All right. Hello and welcome everyone to this webinar on assessing and protecting critical infrastructure. My name is Wetzels, and I'm an embedded security researcher, mainly in the areas of industrial control systems, automotive systems, and IoT. And I formerly was a researcher with the University of Twente focused on the protection of critical infrastructure. I've been a conference speaker at several international conferences like Blackout, DEF CON, and the CCC. And this is my colleague.
Hello everyone, my name is Razvan. I'm a senior certification specialist at Secura, and I'm experienced with several security domains from a perspective of standards and certification, such as ICS SCADA, medical devices, automotive, consumer products, or financial and payments. Before we start our webinar, I would like to tell you a couple of quick words about Secura's internal organization. We are a security center of expertise with several service lines, which are the security testing and assessment, security organization, and on top of that, we address for both testing and organization the issues of security assurance and certification. Besides that, we also offer training and awareness services, and actually this webinar is part of our training service offerings. So now I will switch back to Jos, who will start the first part of the webinar with a bit of a technical description of ICS SCADA.
All right, so a little bit of a roadmap for this webinar. We'll start off with an introduction to the world of industrial control systems before discussing the threat landscape and the attack surface related to that. Then we'll delve a little bit into understanding cyber-physical attacks as part of impact analysis and doing some threat modeling and impact analysis itself. And then I'll hand the word back to Razvan again on addressing risk with standards. Now, if you have any questions during this webinar, please don't hesitate to use the webinar software to ask them, and we'll address them at the end of the talk. So, what are industrial control systems? Well, basically, they're the systems that power the backbone of society, and they are everywhere, whether it's electric power, transmission and distribution, oil and gas, water treatment, nuclear, or systems like infrastructure and transport, mining, or building automation. The building you're probably in right now is hooked up to various kinds of industrial control systems for HVAC and cooling and stuff like that. You're interacting with industrial control systems every day of your life. Now, when talking about ICS, there are two major domains. One of them is the information technology or IT domain that you're all probably familiar with. And that's composed of the systems you know. That's Active Directory, that's the corporate LAN, that's file services, mail services. And then there's the domain of operational technology, or OT, which is where the SCADA network and the RTUs and the PLCs live. And these two domains are increasingly converging, but they still have very different skill sets and mindsets associated with them that you need to understand in order to properly secure them. So OT is essentially about control loops. What this means is that you typically have a sensor that measures some kind of process state, like temperature, flow rate, or something like that, and that's transmitted to a control system that then computes control commands based on this process state for actuators like valves or motors or drives or stuff like that in order to influence the process to adjust its behavior towards a desired state. An example of this would be a temperature control loop. Here you can see a vessel containing a liquid that needs to be at a certain temperature, and you have a sensor hooked up to a transmitter, and this sensor essentially reads the temperature as a process variable and transmits it to the controller. And the controller also has input from a so-called set point. In this case, for example, a thermostatic control that indicates a desired temperature. And the controller will compare the current state of the process variable to the set point in order to steer it towards this desired state, which it might do by actuating a valve to a fuel burner in order to increase the temperature or stop increasing it. And essentially this constant loop of measurement, adjustment is the basic building block of any kind of industrial control system. And these basic blocks are integrated into larger process units that form a large process together, as you can see, for example, pictured in this slide. These processes are governed by industrial control systems of various kinds of architectures. Now, these architectures are increasingly blurring, so you see a lot of the terminology being used in a mixed up fashion. You will have people talking about PLCs, DCS, SCADA, all the terminology in a mixed fashion. But when you're talking about like the pure archetypes, one of the most famous ones is a distributed control system, where you essentially have a bunch of controller elements across various subsystems, usually within different areas of a single site plant, controlling a large number of control loops in a top-down fashion. Alternatively, you have a supervisory control and data acquisition, or SCADA architecture, though the lines in terminology are a little bit blurred, as I said. Now, this has its origins in the remote monitoring and limited controls of systems spread across a large geographical area, typically including many unattended sites like power substations, wellheads, pumping units, and pipelines that would typically require regular field trips by personnel. But with the introduction of remote terminal units, sensors, and actuators that could be hooked up to them, data could be sent to and from the RTUs to a master terminal unit, a controlling PLC, or a human-machine interface across wide area network communications over a broad spectrum of channels like modem, cellular, or satellite. Now, one of the things that most people unfamiliar with the world of ICS will ask is, surely such critical systems are safely air-gapped, right? Well, wrong. This is a very persistent myth that people will need to face that, it's just that. It's a myth. As Stefan Woronka, the former ICS security director of Siemens, said, forget the myth of the air gap. The control system that is completely isolated is history. Now, how did this situation come to be? How did we get from a situation of isolated, relatively non-digitized control systems to a very networked world? Well, a simplified modern ICS network would look a little bit like this. At the lowest levels, mapped onto the Purdue model, you have the field devices, your local and your remote IOs, which are connected to PLCs and DCS controllers, on a control network, which is in turn overseen by HMIs, human-machine interfaces, DCS workstations, and so on, residing on a plant network, which in turn communicates to the office network, which is the IT side of things. Now, traditionally, a lot of these communications in ICS went over current loops or point-to-point serial connections, resulting in a closed system among trusted nodes. And the security legacy of ICS systems really originates here, which is where the pain all comes from. Now, as time progressed, increasing amounts of connectivity were introduced, starting with the advent of fieldbus protocols such as Modbus, Profibus, Foundation Fieldbus, and then we got the Ethernet-based field buses like Ethernet IP, Profinet, and stuff like that, before seeing a lot of wireless sensor node connectivity. And the increase in connectivity here is one of the factors driving the so-called IT-OT convergence, where a traditionally clear separation between these domains is getting increasingly blurred. That's something that's set to accelerate with the advent of the so-called industrial Internet of Things. Now, all of this is being driven by very real operational benefits. So it's not just, a spur of the moment thing. It's something that is set to accelerate and set to be here for a long time to come because there are predictive maintenance benefits. There is the option for real-time decision making. There is increased options for commercial off-the-shelf integration of software and hardware. So this is a situation that we'll need to learn to live with. So these days, when we're looking at an ICS network, we're really looking at a highly diverse network of networks. If you look at the picture, you can see an example where at the lowest field level, you'll have the current loops hooked up to fieldbus communication, hooked up to Ethernet-based communication, to wireless sensor nodes all across, a site or maybe a large geographical area. And all of this is connected by various gateways, which have various levels of security posture. Now, this brings various challenges with it. And the first of these challenges is increased exposure in general. The example on the slide is very extreme, which is a water filtration system HMI exposed to the internet without any sort of authentication. And if you're familiar with the Shodan search engine, you'll find a ton of interesting stuff like this. But exposure can be more subtle than direct exposure to the internet. It might be that you have your operational technology network shielded from the internet, but it's connected to the IT network in a way that allows an attacker who compromises the IT network to easily pivot into the operational technology network. And of course, there's issues around wireless sensor nodes that might be reachable outside the physical facility perimeters as well. You might want to take all these things into account when evaluating system exposure. Now, another challenge is that of asset management. Traditionally, asset discovery and management capabilities are very limited in industrial control systems. And this limits your visibility, knowing what systems are actually there on your networks. It also limits the ability to centralize, apply policies and patches, to push them out in a fashion that we're used to in the IT world. It also complicates risk assessment. If you don't know what is there, if you don't know what communications there are there, it's very hard to make a proper risk assessment. And this problem is compounded by a general increase in assets for all sorts of purposes, especially with the advent of industrial IoT sensors. And finally, another big challenge in ICS security is the sheer diversity and opacity of protocols. There are tons and tons of proprietary, undocumented protocols in ICS systems. A single DCS might have dozens of protocols that are very, very ill understood. This hinders several aspects of a mature security policy. It hinders monitoring. If you don't know what benign traffic looks like, it's very hard to see what malicious traffic looks like. It hinders security assessments. If you need to decide whether a certain protocol is secure, if there are potentially dangerous operations in there, if you need to design firewall policies, you need to know how a certain protocol works. And it hinders incident response. If something does happen and you have the traffic captures, they might be useless if you don't know what happens inside of them because you don't understand the protocols. And all of these challenges help to create a sort of perfect storm for ICS security that require very specialized knowledge to address. So let's take a little look at the threat landscape and the attack surface that's actually out there before moving on. Now, in almost any talk about ICS security, it seems almost mandatory to mention the big S, Stuxnet. For those of you unfamiliar with it, Stuxnet was an attack on the Iranian nuclear enrichment program that actually physically damaged some of the facility. And why do I mention it? Because it really was the watershed moment. It showed that cyber physical attacks, that is attacks taking place in the digital realm with physical results, were taking place. They were occurring, people were doing them, and they were actually possible. And within a few years of the Stuxnet attack, we started seeing the first publicly known reconnaissance activities aimed at operational technology. And now in the last few years, we're really seeing publicly acknowledged cyber physical attacks causing damage or attempting to cause damage. The most famous of these are the two attacks on the Ukraine power grid, which caused blackouts in 2015 and 2016, and the Triton attack in 2017, where an attempted attack to damage physical equipment in a Saudi petrochemical facility was uncovered. And this is definitely an upcoming trend, so to say. Now, when considering the threat landscape, let's take a look at risk. Risks are essentially composed of three factors: vulnerability, impact, and threat. The possibility that something can occur, the fact that this thing can have a negative impact of a certain degree, and someone out there who can make this happen. And this someone, this threat, is itself composed of three factors: intent, opportunity, and capability. The desire to make something happen, the chance to do it, and the capability to follow through on this. Now, when we're talking about threats, one of the first motivations is espionage. And this can range from corporate intelligence, like obtaining information about business deals, to theft of industrial designs or chemical formulas, operational information for competitive advantage, or maybe geopolitical goals, if you're looking at state-sponsored attacks, or maybe reconnaissance for sabotage operations. And these are, of course, the most feared result of any ICS-related malicious activity. Sabotage operations can be very varied. They can be damage to equipment, like pipelines or vessels, or damage to production, like interruption of manufacturing, spoilage of quality. It can be damage to the environment, which in itself is very terrible, but also brings with it very big damage to public relations, as well as potential fines. The attacks can be aimed at denial of service by causing blackouts in the grid, or even injury and loss of life. Now, many people, when looking at physical damage scenarios, they will think, sabotage, I'm not an interesting target, that won't happen to me. But it's not just about sabotage. It's about sabotage as a potential, because sabotage can be used as a threat to leverage in extortion attempts. Alan Peller of the SANS Institute already said a decade ago that successful extortions of utility companies using SCADA systems were occurring, and that the criminals involved had obtained hundreds of millions of dollars successfully to keep this quiet. And this kind of extortion, he said, is the biggest untold story in the cybercrime industry. So the threat out there is very much a real one. Now, when you're evaluating threat actors, you need to consider them across various axes. And one of these axes is opportunity versus capability. And this means that if you are evaluating what kind of threat is posed by the outside world, you evaluate a script kiddie sitting in his bedroom very differently from a disgruntled insider, especially if he's an engineer with access to piping and instrumentation diagrams or engineering workstations, let alone a state-sponsored attacker who has plenty resources. You also evaluate very differently if you're considering opportunistic attackers versus advanced persistent threats. An opportunistic attacker might cast a very wide net, such as using a default credential scanner for remote desktop or VNC access or using Shodan. But a persistent attacker that actively targets your organization can use very carefully crafted spear phishing or watering hole attacks using open source intelligence and social engineering tailored towards your organization. And hardening against that is a very different ballgame from hardening against attackers that use basically an anything goes wide net. Now, another axis to take into consideration is whether you're dealing with commodity threats or ICS-focused threats. When I'm talking about commodity, I mean threats that are not tailored to any environment or any particular target. One example of this in the IT world, and you also see this in OT, is rampaging ransomware worms. Now, imagine all the workstations in your environment that are running outdated versions of Windows. If a ransomware worm gets in there, uses Eternal Blue or some other vulnerability to actually compromise them and lock them with a ransomware attack, how well prepared are you to handle an event like that? This is not an attacker actively targeting you. You might not be, as interesting as people think, but it still might happen to you. This is, of course, a very different situation to deal with than if you're dealing with tailored attacks like Stuxnet or Triton, which are sabotage-oriented malware by knowledgeable attackers. And dealing with a situation like that takes very different knowledge from dealing with commodity threats. You all need to take these things into account. Now, when considering risk, determining impact is of crucial importance here. Something that has a low likelihood of happening, but an extreme impact when it does might warrant more attention than something which is more likely to occur, but has negligible impact. And especially in the ICS world, it's important to realize that impact is always relative to the process. So while you can probably all agree that explosions, blackouts, and transport accidents are high impact, it might just be the case within an organization that the theft of trade secrets, production spoilage, or process downtime is actually far more damaging than the simple damage of equipment. So you always have to contextualize potential impact in order to assess these risks. Now, there can be a very real threat with a potentially serious impact out there, but for it to be considered high risk, there need to be vulnerabilities that can be exploited. In order to look at that, we need to look at the attack surface, the totality for which in ICS environments is absolutely massive. You can see a simplified version of that in the slide, and this would cover everything from regular IT assets in the corporate network to the firewalls enforcing segmentation, or the PLCs and the RTUs at the control and the field levels of the Purdue model. Now, you need to take all these devices into account, as well as the attack surface of the devices themselves and the connectivity that they might expose across various channels. And when looking at the vulnerabilities in the ICS world, it's no secret to anyone familiar with this world that the security is generally quite poor compared to the IT world, often being years, if not decades behind. And the number one issue here is what is called insecure by design. It's not that these systems are designed insecurely, it's that they were never designed to be secure in the first place, because they were designed to be deployed among trusted nodes, not for hostile environments. But the environments that they are used in have become hostile over the years without them catching up. One of the big problems is that equipment like this tends to have very long lifespans of years or even decades, meaning that you'll find plenty of legacy devices or software that's deployed in the field and vulnerable to insecure features or bugs that are very old and well known without the ability to quickly patch or upgrade equipment. So you need to be able to deal with situations like this. And that's very different from the IT world. Now, the second issue, which compounds the first, is that we see a lot of insecurely configured networks. Networks tend to be flatter in practice than on paper, and just because you think you have segmentation going on doesn't mean that you actually properly enforce it. Just because nobody in regular usage connects from A to B doesn't mean that it cannot happen. What we also see is a lot of insecurely configured remote access, either for maintenance or integrators or vendors who have direct access deep within the operational technology networks that might be properly segmented, but if this connection is insecurely configured or the party that has access to your OT networks gets compromised, you might still be in big trouble. You need to take that into account. And then there is the risk of infected USB devices or contractor and support laptops, bring your own device policy being introduced in your environment. You can have a very walled off environment, but if some contractor walks in with a laptop that is insecure or that is infected and then gets hooked up to the soft underbelly of your systems, you're in big trouble. One thing that we're seeing in recent times is that we're seeing the rise of smartphones and tablets with HMI and engineering software on them. And this exposes access to systems on platforms that might not be locked down, or they might even get physically stolen or lost, and you all need to factor this into your security policies. Now, these three issues are just the tip of the iceberg. There are many other issues: lack of personnel training and awareness, lack of asset and patch management, like unsupervised routers, switches, and firewalls, lack of monitoring and visibility, like I mentioned, flawed identity and access management. In many cases, with ICS security, there is a paradox that the issues are simultaneously simple and hard to resolve due to the involved nature of the environment. And resolving this in a proper manner requires specialized knowledge and care to take into account. So we need a way to address all that risk, but before we delve into that, we'll take a brief detour into understanding cyber-physical attacks. While cyber-physical attacks are only a subset of the threats against ICS in general, we need to understand their involved nature in order to perform adequate threat modeling and impact analysis later on. We need to be able to think like an attacker in order to stop them. Now, cyber-physical attacks essentially are about compromising an industrial control system in order to cause physical damage. And there's many different ways to go about this, but at the heart of all such attacks is a so-called damage scenario. And these scenarios are often process-specific, but there are some shared fundamental principles. And one example would be an attacker attempting to create what is called a water hammer effect, as you can see on the right of the slide, where an attacker tries to close a valve at a certain time in a certain manner in order to cause a pressure wave to damage the equipment. Other examples would be causing overfilling of a tank, causing wear and tear on moving parts, or inappropriately increasing the heat or releasing chemical compounds that should not be mixed. Now, what is very instructive in coming up with these scenarios is studying actual industrial accident reports from the industry in question, and then trying to reverse engineer a scenario that leads up to it by compromising the devices and causing it artificially rather than naturally. Now, when discussing cyber-physical attacks, there are generally two common types of responses. One of them is people who claim that they are trivial, they're imminent, the world is about to collapse, we're all going to end up with some Mad Max scenario, and they point at the rather terrible state of ICS security for this. And then there is the other side of the coin, which is people who say it's borderline impossible. They point out how the processes in question are engineered for safety and how involved and complicated such attacks actually are. It can never happen. Now, both of them are wrong. With regards to the first response, it's important to realize that compromising ICS equipment is not the same as winning. When you typically hack a server or you hack a desktop, you get the information, you win. But that's not the case in ICS security. Compromising a network or a PLC is only a small part of the overall cyber-physical attack. And with regards to the second response, while certain cyber-physical attacks are most certainly complicated and costly to develop, it's important to realize that safety is not the same as security. The former does not take an actively malicious actor into account. An umbrella might shield you from the rain, but the rain isn't actively trying to circumvent the umbrella, which is what is happening here. We've seen in the attacks on the petrochemical facility in Saudi Arabia that safety controllers and equipment can be compromised too. Are you sure that any independent dumb fallbacks are sufficient when your safety instrumented systems fail? You need to take that into account. Now, cyber-physical attacks are very process-specific or even facility-specific. Causing a blackout is not the same as spoiling a chemical batch or causing an oil pipeline rupture. In order to carry out an attack like that, you need very good process comprehension. You need to know what causes the right pipeline to explode at the right moment. You need to realize what the uncontrollable side effects of your actions are. You need to realize what safety mechanisms and alarms might kick in to prevent the attack from succeeding. And in order to prepare for an attack like that is where espionage and reconnaissance activity matters. So if you're dealing with an espionage or reconnaissance threat, that might be part of the lead up to a cyber-physical attack. If attackers are getting away with piping and instrumentation diagrams, with historian databases, software and firmware versions, all of that might be preparatory for something even worse. Now, how do we deal with this situation? There's a lot of gloom and doom, but there is a way to deal with this, and that's where threat modeling comes in. Now, threat modeling is a method to analyze the attack surface, which can be done during the development of a new system or can be done during new acquisitions or replacements within an existing system. And here you essentially identify threats by thinking like an attacker and then determine countermeasures and mitigations to address these issues that you uncovered. Threat modeling has roughly 4 major steps, and the first of these is the creation of data flow diagrams. And these data flow diagrams can be constructed at various levels of technical depth, starting with a high-level contextual diagram and then moving towards increasing granularity. And in these diagrams, data flow between various processes and entities is mapped out and trust boundaries between them, which you can see on the slide, are drawn. And this helps us get a map of the terrain, so we know the lay of the land and we can focus our attention on the most pressing areas to prioritize our assessment, especially in environments that are as big and complicated as many industrial control systems. The step after that is identifying the threats for which there are various methods, such as STRIDE, attack trees, attack libraries, and so on. Now, one of them, STRIDE, evaluates threats by categorizing them in 6 different categories. Spoofing, where the attacker forges identities or data. Tampering, where attackers manipulate existing data. Repudiation, where attackers avoid traceability of their actions. Information disclosure, where confidentiality of data is violated. Denial of service, where attackers violate availability of a service. And elevation of privilege, where attackers obtain data to perform actions outside the permitted boundaries of their original context. When applying STRIDE, we start with communications that traverse the trust boundaries and analyze the threats per element in the constructed diagrams for each of the STRIDE threats, coming up with attacker scenarios for achieving them. Now, when doing threat modeling, it's important to realize that the impact is always process-specific, like I mentioned. A pipeline leaking water is not the same as a pipeline leaking flammable liquid as a result of a physical damage scenario. And ruining a production run in a high-value chemical batch process is not the same as ruining a production run in a low-value discrete manufacturing process. The failure of uninterruptible power supply or HVAC in an office area is, it's inconvenient, but it's not the same as that same failure in a data center. You need to take this impact analysis into account to properly prioritize your threat modeling. Now, you do this by finding the parts of the process where failure leads to disaster. Those of you with a background in operational technology will remember the Texas City disaster and the Deepwater Horizon oil spill. And here, issues like splitter tower overfilling or blowout prevention mechanism failure are really the holy grail of the attacker that you kind of want to prevent. Luckily, from the OT world, we have things like process hazard analysis that can inform our impact analysis. By seeing what can go wrong and what can lead to absolute disaster, we can determine attack paths leading up to the situations and then prioritize our assessment along those attack paths. And that really gets that much more efficiency out of your security investment. After threats have been identified, the next step is addressing them and validating them. You can address them by mitigating them, eliminating them, transferring risk. And after you've done this, you validate them by checking, are the mitigations applied? Do the mitigations have the desired effects? Do the mitigations create any additional vulnerabilities that we need to take into account? Now, there are too many ways to deal with threats to go through all of them, but an important one is security zoning, especially in the ICS world. If you have this soft underbelly of insecure by design devices, it is of paramount importance to create zones and defense in depth to protect this soft underbelly. This is typically done by creating security zones. Here, assets, systems, and users are separated into zones, which can be physical groups based on physical locations or logical groups based on functionality or shared characteristics. And then these zones are connected by conduits, which can, again, be physical, cabling, switches, routers, firewalls, that kind of stuff. Or they can be logical, consisting of industrial protocols, database communications, or file sharing. And then the idea is to isolate the assets, the systems, and the users into zones and then control the data flow within and between them to minimize the exposure of the attack surface and build defense in depth in order to limit lateral movement between these zones. Now, zoning is important, but zones are just logical constructs. What you need to do is you need to properly segment your zones and enforce that segmentation. And that you do that by establishing a perimeter around your zone, limiting the number of entry and exit points, and then funnel all traffic through those exit points between the different zones, and then select there by inspecting them, monitoring them, and blocking if necessary. In order to properly do that, you need to have a full picture of all the chatter that's going on, all the traffic between the different assets, all the traffic between the different workstations. Is there any traffic between different nodes in different zones that is not going through these choke points? And you need to eliminate that and properly segment there. Another point of importance that's often forgotten is that the perimeter guardians, the firewalls, the VPN concentrators, need to be hardened and actually managed. If you have a firewall but nobody ever checks the logs, it's of not much use. If you have a very expensive switch but the firmware is 5 years out of date, an attacker might just pop it, with all the ease in the world and break through your precious segmentation. So these are all things to take into account when you're doing a security assessment of your ICS environment. Now I'm going to hand the word to Razvan, who will discuss addressing these risks with standards.
Thank you very much, Jos. We've been discussing a lot during this webinar about threats and the risks applied to the ICS SCADA environments. And at a very high level, those threats and risks have two very important characteristics. The landscape of threats is very complex, and at the same time, the threats and the risks are impacting all the stakeholders involved in the ICS SCADA domain. And when I'm talking about stakeholders, I refer to manufacturers, system and component integrators, and of course, end users making use of operational technology. From an awareness point of view, what we see currently in the field is that in most of the cases, awareness is there. Those stakeholders are aware that in case they ignore security, they're very likely to be exposed to high risks and high threats. However, what we currently see is that we are kind of stuck in a circle of pointing fingers towards who should drive the security advancements. And the parties involved in this circle are regulators on one side, so government, but of course also manufacturers of technology and end users. If we take a look at those parties and we analyze them one by one, from a regulations point of view, we see that currently regarding security, there are no real clear initiatives of regulations in the field of ICS SCADA, which simply means, long story short, that currently most of the pressure and the responsibility is put on the shoulders of manufacturers and end users in order to produce and securely use ICS systems and components. But then, of course, the question is, how can you start? How can you, as a manufacturer or user of operational technology, know that your products and systems are sufficiently secure? Here's where we believe that standards are and should be a strong tool for approaching this issue. Of course, standards, and especially internationally recognized standards, have the biggest advantage that they provide validated technical guidance on how to establish security features on one side, but also security processes and procedures on the other side. But besides that, they also have two very important characteristics. And those are the fact they provide consensus on what are the relevant items, and at the same time, they provide a common language and a set of objectives which could be shared across the involved stakeholders in a particular domain. And as we saw, specifically in the domain of ICS SCADA, this is very complex and there are so many stakeholders such that it's really important that we have a common way, a common language and a common set of objectives that all of those stakeholders share. This is how we can address security from an efficient point of view. And this is what we believe that standards could really be the most important way to start. Talking about relevant publications, well, fortunately, in the domain of ICS SCADA, there are quite a few, and the ones that I selected on this slide are just a couple of examples of what we believe to be currently the most mature, the most relevant. Examples include the IEC 62443 family of standards, which we're going to talk about also in the next couple of slides. Also the UL 2900 family of standards, especially part 2-2, which is addressed for ICS SCADA systems and components. And then on a more organizational point of view, we have publications such as the NIST Cybersecurity Framework or the NIST Special Publication 853, or the Dutch local ICS SCADA security checklist issued by the NCSC. So basically, we're not lacking publications. We seem to have them. However, what we see is that from a quite strange point of view, the simple fact that we have so many publications, it's actually one of the reasons why standards are currently not that well adopted into the field. And that's simply because for you as a manufacturer or as a user of technology, it's quite difficult to identify the best source and to start applying it in an efficient and quick point of view. Manufacturers simply, and most of the times, don't have the expertise or even the time and budget to make such a big research. And actually, this is one of the issues that we at Secura identified as well, and we actively spend time in researching the domain of available publications in order to select the best possible starting point. Of course, there's no such thing as a best standard, but for selecting a starting point, we came to the conclusion that the ISC 62443 family is actually that starting point that you're looking for. And the reason why we believe that is that this family of standards, which, as you can see on this slide, consists of in total 13 publications, 13 standards. This family is addressing ICS security from a holistic point of view. As you can see, the standards are grouped into 4 categories, starting with general concepts, then going towards the soft side of control system security, which is more on the policies, process, and procedures side, but then also addressing security features, technical security features on the system and component level. At a very high level, the standards of this family could be split into 2 main categories, and those categories would be the standards addressing organizational procedures, so again, more on the logical process side, and then standards which are addressing technical security features. On an organizational side, we have ISC 62443-2-1 addressing security processes and procedures for maintaining your ISMS. So actually the standard is quite in line with the requirements of the ISO 27001 standard. Besides that, we have ISC 62443-2-4 addressing security procedures and processes for secure integration of ICS systems and components. And finally, another relevant one that I extracted is 62443-4-1 addressing secure development procedures and processes for components and systems. So more focused on the manufacturer, to the manufacturers of technology. And then from a more technical point of view, we have ISC 62443-3-3 and -4-2, which are addressing technical security requirements focused on the security features of systems and on component level. The scope of those publications is a bit outside the scope of this webinar, unfortunately, simply because there are so many standards and it's difficult to summarize all of them. However, just to provide some examples, we selected two standards which are presented on this slide, and the selected ones are actually covering on the left hand side more the process and procedures part. So that's ISA 6443-2-1, and then on the right side the more technical security requirements for systems and components. And if you take a look at the examples of topics which you can find inside those standards, you can see for the more process-oriented one that you can find requirements about risk analysis, defining and drafting of security policies, security awareness within your organization, selection and implementation of security controls, and of course monitoring and improvement of your ISMS. So once again, you can see that those requirements are really quite in line with the requirements of the ISO 27001, but more adapted to the ICS SCADA domain. And then from a more technical point of view on systems and components security, we can see that topics which are addressed for defining security requirements are, for example, authentication and authorization of those systems and components. At the same time, data integrity and confidentiality, but also industrial specific topics such as incident response of your component or your system, or system and component availability. To sum up on the benefits of this ISC 6443 family, of course, I would start with the fact that it provides really state-of-the-art validated requirements. Actually, this standard is at this moment quite a hot one, if you can put it this way. And for sure, you can find a lot of people mentioning about this family of standards if you are going to conferences or workshops or other meetings. It is very internationally recognized, very talked about. And finally, what we really believe that it's maybe, besides the technical contents, maybe the most important feature is that it addresses the whole security supply chain of ICS SCADA from a holistic point of view by addressing standards and requirements individually for manufacturers, system integrators, and end users. And therefore, by doing that holistic approach, it addresses exactly the goal of having a common language and common set of objectives from which we actually started. And this is why we believe that ISC 6443 should be a very important stepping stone towards improving security in your systems or components. I will end my part of the presentation by briefly mentioning about the issue of security certification in the field of ICS SCADA. Of course, so far we've been discussing a lot about security standards, and definitely adopting a standard is a very important starting point, which we totally support and totally encourage. At one point, for you as a manufacturer or user of operational technology, there will be the question of how can you make sure that the requirements of a standard are completely and even maybe more importantly correctly implemented in practice. And here's where certification could really be the solution. Certification in most of the cases is done by an independent organization, which is taking a look at how you are implementing those requirements. Currently, in the world of ICS SCADA, there are several active security certification schemes, and examples of those would be ISA Secure scheme or IECE. Both of those schemes, which have ISA 62443 in scope, so they're actually designed across in line with the requirements of this standard. And besides that, currently at European level, we have a concrete initiative of establishing a security certification framework focused on the security of industrial control systems and components. Secura is actually part of the team who is driving the efforts over there, and we do expect that the scheme will become available and live for projects somewhere maybe in the second part of next year. And this scheme is going to be also based from a security requirements point of view on the requirements of ISA 62443 standard. Now, before we finish this webinar, I would like to point your attention to the Secura dedicated 2-day ICS SCADA training, which we devised simply because I think both Jos and I had many topics that we wanted to talk to you about. But well, simply fitting that into this 45 minutes webinar is not that easy. So as a matter of fact, we have designed this dedicated 2-day training, which is covering topics which are very in line with the ones which were covered during this webinar. So you could see the webinar as kind of a teaser for the training. But during this 2-day program, you can find a lot more details about IT and OT security, specific examples of threats landscape and attack surfaces, also with practical demonstrations, and a lot more details about state-of-the-art in standards and certifications. So the training is supposed to be organized somewhere in the very early beginning of next year, so probably around January. So I would advise you to stay tuned to the website of Secura for more details. And with that, I would like to thank you again for your attention. Thank you, Jos, for contributing. And at this point, we are willing to answer the questions that you might have. And I have a first question here. The question is, do you know any attacks or metering or readout monitors to create incorrect behavior by the technicians and have them inflict damage on the organization itself without knowing it? And that will be a question which I think is addressed to Jos.
Yeah, so there are many different kinds of attacks on industrial processes possible. It's possible to engineer an attack scenario where you cause the damage fully yourself, but it's definitely possible to allow inadvertent information in an industrial process to cause the damage as a secondary result. So one thing we will cover during the training is the so-called cyber physical attack tree, where you have various aspects of attacks on industrial systems. And one of them would involve blinding or misleading operators into taking a certain action that is unintended as a result of readout values. And it's interesting that the question mentions sensors and metering, because at the level of field devices, there is absolutely no security. We have seen some improvement in PLCs and controllers, but none so far in sensors. And these are getting increasingly networked, communicating between each other, being exposed even sometimes to the cloud with some of the newer smart ones. So this is an upcoming, very important problem that definitely requires in-depth attention.
Thank you very much, Jos. We don't have any other questions currently recorded. So, well, anyway, we do encourage you to get in further contact with us for addressing any other sorts of questions about ICS SCADA. on a more threat analysis and landscape. I'm quite sure Jos can offer you a lot of input if you can get in touch with him, and then I can provide the same thing about the standards part. But actually, we do have another question which is coming up right now. I will read it out loud. As we know, many ESD vendors, for example, Yokogawa, Honeywell, Schneider, have different implementation in DCS or SCADA systems. What do you think about What do you think about this issue?
So the question is relating, I get to emergency shutdown systems. Or I can properly read it, but yeah, many ESD vendors. So the problem is that there are many different implementations from many different DCS or SCADA vendors, and addressing security among them will be a tailored effort. So it is impossible to basically come up with a one-size-fits-all policy that suits everybody and everyone. It will be a tailored effort not only towards one specific vendor solution, an integrated DCS solution, but towards one specific facility or industrial process where you need to take the whole process holistically into account and then subsequently work from there with all the nuances that are vendor specific in that regard. So this is it's definitely bespoke work, not something that can be addressed in a very generic fashion, saying this is how you secure ESD.
Thanks a lot, Jos, and thanks a lot, Murat, for raising this interesting question. As a matter of fact, Murat has raised a second question, which asks, can you evaluate in terms of network security? I will try to start an answer to this question more from a standard and an assessment point of view, and maybe later you can add something if you think relevant, Jos. If we take a look at, for example, the family of standards that we've been discussing about, and that's IEC 62443. Like I said, this family of standard is comprised of many individual parts. And one specific part, which I also briefly mentioned, is IEC 6443-3-3. And this is focused on providing security requirements for system security. What it does is that it sees the systems as really everything that is inside an ICS infrastructure. Of course, you can scope it in different ways. So you can have smaller scoped systems, or even you can see your whole infrastructure as a system. But definitely, network security requirements are part of the standard. For example, just a brief example of a topic is the fact that secure network segregation, so splitting a network into security relevant and not security relevant parts, is one of the security requirements which is addressed by the standard. So then the question is yes, from a standardized point of view, you could address network security in a similar way as you address component security.
Yeah, and to add on to that, when it comes to network security, to briefly also touch on the previous question, like it's no big secret that not only the devices but the protocols themselves are insecure as well. So if you're talking about like the DCS protocols, Yokogawa, Emerson, any other the big vendors, they have insecure protocols. So how do you deal with that? Well, the key aspect within ICS security is always zoning and segmentation. So contain things within a proper zone, segment those zones in the proper way, and ensure that any insecure communications that leave a particular zone are transferred across a secure transportation. So do anything, if it's possible, transport it across VPN connections. Make sure that if you're able to wrap a certain protocol within SSL, then wrap it within maybe a null cipher with authentication on top of it. It's hard to give a general answer because, again, it's going to be very process and facility specific. But in general, what you want to do is isolate, concentrate, and then at the few choke points where you can really monitor and really control, apply those central security controls there to make sure that you don't have this jungle of insecurity that most traditional ICS environments are.
Indeed, and exactly parts of the IEC 64433 standard about system security are definitely a correct zoning system and a correct network segmentation implementation. And in fact, one of the biggest values of the standard, which I didn't mention before because actually it involves quite a bigger discussion, but very high level, the standard is designed in such a way that it implements different security levels. So besides the fact that you should split your system, your network into zones based on risk, then also you can assess the risk of those zones and end up in one of the defined security levels based on the standard. And then the requirements, the security requirements from the standard are actually tailored on that specific security level. That's one of the extra values of this particular standard. So thanks a lot for the question. It's actually a topic on which you can discuss quite a lot.
Yeah, definitely.
I see no other questions at this point. So once again, everyone, I would like to thank you for tuning in and for listening to this webinar. I hope you found it interesting, and of course, we do encourage to keep an eye on the Secura website to see the other training and other kind of services that we offer. Thank you very much for your attention. Thank you very much, Jos. So I wish you everyone a nice evening.
All right.